Okay, so this study is another example of a two-way mixed ANOVA. The actual study itself took 15 climbers. They were elite boulderers, and they were randomized into three treatment groups. If I just click the toggle button, we got 5 in control group, so they took their normal training, and then 2 groups with a specific strength training exercise for the grip. One was to maximum 5 seconds grip strength protocol, and the other was 10 seconds isometric grip protocol. Okay, so a slight difference in duration of maximum contraction. So we measured 2 parameters, 2 variables. One was the maximum crimp grip, and the other was critical force. The first one was a measurement of strength, the second one is a measurement of strength endurance. It's been run over a pre-post design, so hence the reason why it's a mixed design, because we've got 2 independent variables. One, in this case treatment, has 3 levels to it. It's a between groups variable, different people in each group, whereas the other is time, and we've got 2 examples, 2 of the dependent variables. We've got a pre-post possibility here, so 2 levels. So it's sometimes understood as a 3x2 mixed ANOVA. Okay, I'm going to skip some of the parts because they're in some of the other videos, normality checking, assumption checking, etc. So let's push on, and I can tell you in this case that we do have parametric assumptions, and therefore we're at liberty to progress to a general linear model approach. So the first thing I want to do is run the two-way ANOVA. So go to a general linear model, and because one of our independent variables is a repeated factor, that's what I'm going to call time. Therefore, we have to choose this option. Add, click define. So I'm going to analyze the maximum volitional contraction of the crimp grip first, against between groups factor of treatment. The choices that you got then is plots. The obvious plot to do is the interaction, and I suggest it's generally a rule of thumb, if you take whichever variable has the most levels to it and place that on the horizontal axis, it can be an effective way of interpreting the change. So I'll place, in this case, treatment on the horizontal and time as separate lines, time being pre and post, and click add. And that's the key one that we're interested in this case. There may be main effects of time by themselves or treatment by themselves. That's up to you too, if you want to make those decisions to include as well. So let's go continue. In terms of contrast, do we want to set any sub-hypotheses? Again, you have to make a decision as to whether you want to look at treatment by itself, irrespective of time. If you do, then you need to select that and make a choice as to what type of contrast comparison to make, what type of pairwise comparison to make. Simple, you're basically comparing all groups to the control group, which is a fairly standard approach. But in our case, I'm going to skip this and get to the main part, which is the interaction. Similarly, you could do post-hocs, of course, for the between groups variable. Instead of contrasts, you wouldn't do both. Finally, we click on the options dialog box for the repeated measures factor, time being the main one that I'm interested in. So I'm interested in this interaction. So I want it to display means, some descriptive statistics, and if you wanted to, you could take the homogeneity test as well, but you've probably already run that. So those are the key areas to have included. Now, if there is an interaction, what SPSS doesn't do is allow you, for more than two group design, to identify where that interaction is, where the pairwise differences lay. So you have to make an addition to the syntax. You can do that in one of two ways. And one easy, simple way is click on paste. It will take you to the dialog window. So this is the general linear model that's being run at the moment. And what I want it to do is, when it creates the table of the estimated marginal means for the interaction, I want it to also do a comparison over time. So what I'm going to do, I'm just going to paste in here. You can do this either, so this is the key text to include, compare over time. You can also add in the Bonferroni adjustment to correct for the fact that you're running multiple pairwise comparisons. And then, because this is not standard dialog, I just added this into the dialog. If I was just to click run, it wouldn't include this from the previous instructions. So the way to do that is to highlight the whole thing and then click the play button here. Okay. So let's interpret the output. The first key area is, we don't have to worry about much this test in this regard, because the repeated factor only had 2 levels to it, pre and post. So that's why there's no sig value here. You need at least 3 levels for that to be important to look at. So first of all, we've got treatment by time, which is the interaction, and that's the main finding that we're interested in. And what we can see is that we have a level of significance which is below 0.05. So we would reject the null hypothesis. We interpret that there is an effect of treatment over time. There's also an effect of time, pre against post, irrespective of which group you're in, but I argue that's of little use, since we're more interested in is there a difference over time because of the grouping being included in that factor. Right, so that's the first part. There is an interaction. The next part really is to also follow that interaction up with a calculation as to, okay, well, where is the interaction? So if I track down and I look at one of the plots that I've created, what we've got here is, in blue, is the pre-scores for the 3 groups. So you can see that the 2 groups here for the control haven't changed much over time. Neither have the 10-second group changed much over time. So it's, from an eyeball point of view, one can see that the difference is probably occurring due to the 5-second group having seen an increase over time. And that difference is around a 2 kilo change, a 2 kilo increase. So statistically, can we see any evidence for this? So this is the part, that the additional line that we added into the syntax. We can see at the control period, comparison between pre and post at levels 1 and 2 is non-significant. And similarly at the 10-second group, difference between pre and post is also non-significant. The difference is coming at the 5-second group between 1 and 2. And here we can see that's a different effect. And obviously we can bear that out in the difference that we see in these comparisons between these means. Statistically, we can therefore give some figures for the effect size calculation. And we can do that from the multivariate test that's also been included as a consequence of that additional line that we put in. And we can look at the 5-second part, and using the degree of freedom, in this case degree of freedom of 1, an error degree of freedom of 12, and an F statistic of just under 29, we can take those 3 numbers. So the F value for the model will go here and here, and the degree of freedom for the error term we place here. So this is a simplified equation we can use when we're just doing pairwise comparisons, and we've only got 1 degree of freedom as a consequence of that pairwise comparison. And then we can use Cohen Jacob-Cohen's interpretation of this Pearson's R correlation coefficient to make an interpretation of the size of the effect. So let's run the calculation. I'll pull up calculator. So what we need here is, I'm looking at the pairwise comparison, i.e. pre against post for the 5-second group. I'm going to do the denominator first, so I take the F statistic, 28.809. Add to that the degree of freedom for the error term, which is 12. That's the denominator. So I'm going to multiply that. I'm going to multiply the inverse of that by the F statistic. So multiply by 28.809 equals, and then we'll take square root. There isn't a square root symbol directly in here, but that's it. I just have to tell it what y is. The square root symbol is, in this case, would be 2. So that gives us a Pearson's correlation coefficient of 0.84. That's a very large effect that we've found for the strength training group. So finally, I want to plot a graph of the findings. Could be a line graph, could be a bar chart. If I wanted to do a line graph, I'd take treatment as the set the colours for the cluster, looking at pre against post, and display error bars. Default 95% confidence. We'll apply that. I'll look at the information currently held on the x-axis. There's no label for that, so I'll call that group. You could call it treatment or group, whatever you feel the right one. Apply. Y, so again you could spell out, rather than just reading currently at the mean value, you can actually say what it is. So this is half crimp grip MBC, and then it's measured in kilograms. Apply. You could also change some of the graph information here. You can do this later, of course. For example, if you know that the values are particularly high or significantly away from 0, you might do that. So let me just put in figure of 50. I know that the results are probably somewhere around 60 kilograms, so I'll apply that. The other thing I would do is click on the titles and footnotes and deselect the footnotes. All titles, any footnotes, etc. You want to put those outside of the graph in the body of the manuscript with the graph themselves. So let's just check that none of this has been lost. Yeah, that's all good. Okay, and yeah. So let's have a look. Now what you notice is that although we've got error bars, we don't have any mean values for the groups. So you'd need to add those. And it's also your choice as to whether you want to express this with treatment as a legend, and rather than time on the horizontal axis. So to do that, what you'd need to do is take treatment and place that here, and then take your values of interest, again back onto the vertical axis. That should still have been held. No, there you go, it's not held the y-axis that I changed. It's also pulled back footnotes as well. Let's see this one. Okay, this is the one that came out in the earlier plot above. So we double click it, send it into edit mode. Let's change the background, transparent, get rid of the border, apply, that's the first thing. And you may feel that you want to increase the size of the text. Let's say 10 and also 10. You could also change the number format here to 0 decimal places if you wanted to. It looks like it won't let me. That's better. Obviously this is running up in 5 kilo differences. If you've got to decide as to that's sensitive enough for you to make interpretations, or if you want, you can change that scale by changing the major ticks or putting in some minor ticks as well. So if I change this to 2, for example, so it's running every 2, it's probably too much. So I think in hindsight we could leave it as 5 in this case. And it's a question of what's not here are the actual values themselves. There's no marker for each of these. So if you click on this add marker, you can see it puts a circle around each of the mean values. And just if I try and select one of those again, there we go. If we click on markers, and what you notice here is that it's locked, so I can't fill it in, and I also can't change the shape. And that's because they're linked together, so to unlink them, if you just click on one of them, in this case I'm just clicking on one of the green, you can see it's deselected the blue circles, now allowing me to change. So I'll change that to circle, I'll make it a little bit bigger so it stands out. There we go. And then again, go to one of the other blue circle, and if you can carefully, there you go, select, fill, and also apply that. And change the size, and I could also differentiate with shape. I could do triangles, okay, or panicles, squares. Okay, I can get rid of this legend by clicking this button here, and there we go. There we've got a line graph showing change between the 3 treatment groups, control, 5 second, 10 second, against pre and post. Okay, there we go.